So now that we've established the threats to biodiversity, we're going to try to shift gears now and fix the mistakes that have been made. We're going to undergo something called population conservation in this lecture, Biology Conservation. So we'll entitle this next flowchart Population Conservation 1 and look at our first approach to conserving populations. So this will be entitled Population Conservation, Roman numeral 1. And the first approach to this conservation process will be through the small population approach. So we're going to start at a small population and try to fix a mistake or try to fix a dying small population, a near extinct small population, through a couple of different mechanisms that work off of conservation biology themes and techniques. So, first and foremost, why are we focusing on small populations? Small populations are quite vulnerable to two different things. Small populations are vulnerable, okay, so they're vulnerable to both inbreeding, so that is not good, that reduces genetic diversity, that really makes things genetically inviable, and also genetic drift. The idea of leaving a population and establishing a new population somewhere else, or not successfully establishing that new population, whatever it may be. So because they're so vulnerable to these key events, these key possible events, we would say that in a small population, it's very likely for an extinction vortex, very nice term right here, to form. So what is an extinction vortex? An extinction vortex is a direct result of the vulnerability that we see in small populations. When we have an extinction vortex, we state that the population gets smaller and smaller till there are no individuals. Smaller and smaller till there are no individuals left. So no INDS for individuals. So you want to avoid getting into this extinction vortex. You want to avoid avoid this idea of this vulnerability and inbreeding and genetic drift. But how? How do you do this? What you have to look at is a very important value, a very important term, that is going to be the idea of the MVP. This is not the most valuable player. It's a term that actually stands for a minimum viable population. So we'll write this down as minimum viable population. And that's where MVP comes from, not most valuable player. So in a minimum viable population, we're going to understand that this is going to be the minimum size for population to sustain life. So we'll say min size for pop to, and there's this key word again, sustain, continue life. So if we get to this min size, then we are on the right track, so to speak. And we can figure out this min size. We can figure out how to get here. It's found with very fancy computer models that utilize highly advanced statistics, let's say. And we'll do a little bit of that statistical analysis right now. So, in order to understand MVP even better, we utilize an idea behind small population approach to population conservation, like effective population size. So we're going to be utilizing the effective pop size in order to conserve a small population. Here, we're going to be looking at how many individuals within a population will breed. That's all we care about. How many individuals within population will breed. That's our key. That's all we care about. That's the population size we care about. That's why we call it an effective population size and not just the population size. So again, this is absolutely not, it is not the total population. The total population is N. But what we care about is only those individuals, how many of the individuals within the population can and will breed. So this is essentially going to be the breeding potential within a population. What potential does this population have? What is the potential of this population to breed? Okay? So we utilize a fancy equation known as the effective population size equation that can be defined as the following. It would be N sub E for effective population size, right? N stands for population size, is equal to 4 times the effective, let's say, population size of the females multiplied by, same thing on the male end, and that's going to be divided by N sub F multiplied by N sub M. Females, males, females, males. We don't need to get into the derivation of this equation. I think the best way to understand the usefulness of this is to just simply do a very basic example calculation as to what an effective population size would look like. So let's imagine the following. Let's look at this example. The example would be a total population that I'm going to give you as a starting population, let's say, of 1,000 individuals. And then within these 1,000 individuals, I'm going to say that this population is with 500 males, nice even number, and of course 500 females, another nice even number to work with. So if we have 500 males and 500 females, I'm also going to tell you that they are all breeding. So they all can breed. Everybody in this population can breed. Tell me the effective population size. And it's a very simple calculation. All you have to do, and we're extended over here, is to get N sub E, effective population size, multiply 4 by 500, multiplied by another 500, and divide that all by 500 times 500, and this will give us 1,000 as our effective population size, just like we would expect, the total amount of individuals that can breed, the breeding potential of our population. How many individuals can breed and will breed, that's what we get from this. It's an important number because it tells us what we need in order to get to a minimum viable population. What are we working with, essentially? What are we working with, and how can we then utilize that to get to the minimum population size to sustain life? In order for this to happen, we usually see a couple of key steps, let's say, in a real life, let's say, nature example. Usually at first, in terms of the steps for a small population to be conserved, in order for us to do this conservation, we first see declining genetic variation. This is just a natural occurrence that happens. Once we see declining genetic variation, we have something to, let's say, try to improve. We can try to fix this through utilizing these population conservation techniques. And whenever something is declining in genetic variation, that would mean it's probably inbreeding or it's undergoing genetic drift, and thus it is entering an extinction vortex. This is simply just the first thing we usually observe in nature, and this is what we're going to try to fix. So that's our step one, to figure out that a population is declining, to figure out that it's in an extinction vortex. What is step two? Next step would be to transfer the population. By this, I mean that we're going to take this population and make sure that there's a transformation of genetic variation. We're going to promote genetic variation. Somehow, some way, we don't need to get into those details. I'm just going to write genetic variation as gen var for genetic variation. And then finally, we would expect to see that the population rebounds. Your textbook has a good example of these step by step in a nice figure. And you can look at that figure and see that step 1, step 2, and step 3 correlate very nicely with the figure's results. So overall, this is our small population approach to population conservation. Big things to understand are the MVP, minimum viable population, and how it's related to the effective population size, what we initially see, what we try to fix, how we try to fix it through these steps.